All right, today we're going on a bit of a detective mission. We're going to trace the secret life of a pollutant, follow its hidden journey from the very moment it hits the water all the way to its final and often pretty far-reaching impact. I mean, have you ever really thought about it? You see a picture of a factory pipe or an oil spill, but what happens next? Where does all that stuff actually end up? It's a huge question, right? So let's dive in and follow the trail. Okay, so our journey begins right at the start. I'm talking about the first few seconds, the first few moments after a pollutant splashes into the water. What happens right then and there?
So there's a big picture term for this whole thing. It's called dispersion. And it's not just one thing happening. It's kind of the umbrella term for how these contaminants start to spread out and begin their big journey through the water.
And the very first thing that happens is dilution. Makes sense, right? The pollutant immediately starts mixing with all that water around it. Now, this does lower its concentration, which can make it less toxic right on the spot, but, and this is so important, the pollutant hasn't vanished. It's not gone. It's just spread thin, getting ready for the next part of its trip.
Which, of course, leads us right to part two. Now that it's all mixed in, that pollutant starts to travel.
See, it's not a localized problem anymore. It's literally part of the water now. It's become a passenger, riding along in this massive, powerful circulatory system of our planet's rivers and oceans. It is officially on the move.
And you can see exactly how this works. It's getting swept along by the flow of rivers, pushed around by these huge ocean currents, even dragged by the tides. Think about it. This is how an oil spill can travel across an entire ocean, or how runoff from a farm can end up contaminating a lake that's hundreds of miles away. The problem might start local, but believe me, the impact can become regional or even global really, really fast.
Okay, but here's where the story takes a bit of a sneaky turn. Because sometimes the pollutant just seems to disappear. It's like, poof, it's gone. This is the invisible threat, the one that's hiding in plain sight.
So how does it vanish? Well, it's a process called adsorption. And the best way to think about it is that the pollutants literally hitch a ride. They physically cling on to the surface of all these tiny floating particles in the water. You know, little bits of clay, some organic stuff. They just grab on. And what happens once they've caught their ride? Well, those particles, now carrying a toxic little passenger, get too heavy to just float around anymore. So, they sink. That's sedimentation. The pollutant settles down, down, down to the bottom, getting buried in the sediment on the riverbed or the ocean floor. And it seems like it's gone for good, right?
Well, out of sight, out of mind? Not so fast. This is the scary part. As this quote points out, those pollutants hiding in the sediment are basically a ticking time bomb. All it takes is one big storm or a dredging operation to stir everything up. And just like that, those old contaminants get re-released right back into the water. And that possibility, that re-release, leads us to what is maybe the most dangerous part of this whole journey. This is where the food chain gets contaminated. This is where life itself gets pulled into the story.
Okay, to really get this, we need to know two key ideas. They sound similar, but they're different. First, you've got bioaccumulation. That's just the buildup of a pollutant in one single animal over its life. But then you have biomagnification. And this is where things get really, really dangerous. It means the concentration of that pollutant actually goes up as you move up the food chain.
Think of it like a ladder. At the bottom rung, step 1, you have tiny plankton absorbing the pollutant. Okay. Step 2, a small fish comes along and eats a ton of that plankton. Now it has all the toxins from all that plankton inside it. Step 3, a bigger fish eats a bunch of those small fish. See where this is going? The concentration is getting stronger. And finally, step 4, a bird or even one of us eats that big fish. And boom, you get a super concentrated dose. The pollutant gets more and more potent at every single step.
So we've followed this pollutant on its entire journey. Now we get to the big question. So what? Why does any of this matter? What's the end game here?
Look, it's obviously a super complex system. I mean, this table just gives you a little peek at all the things that can change a pollutant's journey. Water currents, temperature, you name it. But here's the thing. No matter which exact path it takes, the final destination, it often looks disturbingly similar.
First and foremost, at the end of this journey, our water quality just tanks. And that, in turn, has direct toxic effects on the fish and all the other creatures living in that water. It can even trigger oxygen depletion, which creates these huge underwater dead zones where basically nothing can live. And the ultimate punchline to this whole chain reaction?
a major loss of biodiversity, a completely imbalanced ecosystem.
So what's the big takeaway here? It's that understanding this journey is absolutely critical. It's the key, it's how we can predict a pollutant's behavior, and it's the only way we can come up with real strategies to control pollution and protect these ecosystems we all depend on.
And that really brings us to the final thought. We've just spent this whole time tracing the journey of a single pollutant. So I'll leave you with this to chew on. What happens when it's not just one? What happens when there are billions of them, all taking the same journey all at the same time?